Hi everyone, my name is Joanne Kennedy and I'm a naturopath specialising in the MTHFR gene mutation. So I've put together a presentation with the aim of really breaking down this somewhat complicated topic into what you really need to know. So what we're going to cover is what is the MTHFR gene and how how having an MTHFR gene mutation can affect your health. We're going to look at the importance of understanding your homocysteine levels. We're going to have a look at what is methylation and what impacts methylation from an environmental point of view. We're also going to go through some key blood tests that are really helpful for understanding what's going on with your methylation, as well as some diet and lifestyle tips that you can take home and start implementing straight away. Okay, so what is MTHFR? So the MTHFR gene encodes the enzyme methylene tetrahydrofolate reductase. So that's MTHFR. So this enzyme catalyzes the synthesis of 5-methylene tetrahydrofolate. That's methylfolate, the bioactive form of folate that the body actually uses. So what that actually means is the MTHFR gene provides the code for the MTHFR enzyme. So when we're talking about MTHFR, it's a gene and an enzyme, and the enzyme takes folate from food and converts it into methylfolate, which is the active form the body uses. This methylfolate then goes on to donate a methyl group for the re-methylation of homocysteine to methionine, which is the precursor of S-adenosylmethionine, or which is often referred to as SAM or SAMe, which is a supplement. And SAM is the body's major methyl donor. So this diagram here, this is really helpful to have a diagram to actually see what we're talking about. So here's the MTHFR enzyme, or the gene provides the coding for the MTHFR enzyme, takes folate from food, converts it into methylfolate. Once you've got your methylfolate, it moves up here and it binds up with methylcobalamin, methyl B12. And the reason it does that is for homocysteine to be remethylated to make methionine, and then methionine goes on to make S-adenosylmethionine, or SAM or SAMe, which is the body's major methyl donor. Okay, so what then is methylation? So methylation is a biochemical process whereby a methyl group, which consists of a carbon atom and 3 hydrogen atoms and a spare arm, is transferred onto a substrate, and this includes DNA, RNA, neurotransmitters, hormones, immune cells, and nerve cells. So once these compounds are methylated, they're able to commence their required functioning. So here are some of the functions of methylation. So methylation is really important for detoxification and hormone regulation. So methylation detoxifies estrogen through the liver. And so issues with this can lead to a buildup of estrogen and symptoms such as heavy periods, painful periods, premenstrual dysphoric disorder, which is a really severe form of PMS that I see a lot in clinic. It also is important for the production of neurotransmitters, so this can lead to problems with mental health, anxiety, depression. It's very important for DNA and RNA synthesis and repair, so issues with this can cause miscarriage. It's involved in gene regulation, energy production, fat metabolism, the repair of your cell membranes, and the myelination of nerves. So myelin is the protective coating over your nerves. It's also involved in immune function. And one of the big things that we see is its effect on histamine. So it reduces histamine. This is very important, as if histamine builds up in the body, it can cause a lot of problems such as anxiety, insomnia, headaches, migraines, dizziness, causes eczema and hives, can cause a lot of coughing, wheezing, it can cause issues with the gut. such as bloating and loose stools, and it can also affect smooth muscle, causing period pain. So we can see that methylation is involved in numerous processes in the body. So what happens with a mutation in MTHFR? Okay, so we know a mutation in the MTHFR gene is associated with a decrease in the activity of the MTHFR enzyme. So that's a decrease in your ability to take folate from food and convert it into the methylfolate. So this ultimately results in a decrease in your cellular folate, preventing that remethylation of homocysteine to methionine. Okay, and then what can happen here is that homocysteine rises in the blood, and it's an inflammatory marker, and we'll talk more about that later, but that's not good at all. And you also have a reduction in methionine synthesis, and so ultimately will lead to a reduction in SAM and reduced methylation. So here is Ben Lynch's pathway planner. So this is from Seeking Health Education. And this is, we can really see what's happening with the pathways here. So here's your MTHFR gene. Okay. So what happens is folate from food moves through this pathway, comes all the way down. Once it gets down to MTHFR, it's converted into the methylfolate. Once you have the methylfolate, it moves up here, binds up with methylcobalamin, methyl B12, and homocysteine gets remethylated with the use of methylfolate and methyl B12 to methionine. Methionine then goes on to make SAM or SAMI, your methyl donor. Okay, so we need to understand what can impact these pathways from an environmental point of view. So one of the first things we need to understand is that folic acid, which is a synthetic man-made form of folate, blocks this DHFR enzyme right up here. So it blocks the uptake of your natural folate at more than 200 micrograms a day. So it makes sense if you've got problems down here, you don't want to be blocking it upstream with folic acid. So that's fortified in Australian wheat. It's in a lot of supplements as well, and a lot of processed foods can contain folic acid. So what can happen if homocysteine is not remethylated to methionine, because there's a lack of methyl B12, methylfolate? You build up homocysteine in the blood, and that is inflammatory. It's a cardiovascular risk marker. It damages the blood-brain barrier. You know, there's research around Alzheimer's, causing Alzheimer's. It can cause recurrent miscarriages. It causes blood clotting. So we need to understand that homocysteine is really important. Homocysteine is also involved in this pathway here. So homocysteine is involved in the production of glutathione. So glutathione is your body's major antioxidant. So whenever you have inflammation in the body, so it can be coming from infection, autoimmune conditions, your body uses a lot of glutathione to sequester the reactive oxygen species and the free radicals that occur due to inflammation. And what can happen is homocysteine gets pulled down this pathway to provide the cysteine required for glutathione. So your homocysteine can start dropping. You don't have enough homocysteine to remethylate to methionine. You've got problems with methylation. And you also have an upregulation of this pathway, which is called the CBS or the transsulfuration pathway. And people with an upregulation of this pathway can have problems with an increased production of ammonia. That makes you feel terribly unwell, nauseous, fatigued, terrible brain fog. It also increases nitric oxide, which is a vasodilator, makes you feel, lowers your blood pressure, makes you feel quite dizzy. So this pathway is also what we really need to look at and understand. Over here, we've got all our neurotransmitters. Okay, and we understand that methylfolate is the only form of folate that crosses the blood-brain barrier involved for the production of our neurotransmitters. Okay, so this is some of the conditions associated with methylation issues. So we've got all the cardiovascular disease, cerebrovascular disease, recurrent miscarriage, often due to high homocysteine, but recurrent miscarriage can also be to sort of methylation problems of DNA and RNA and cell replication. We've also got, mental health is big, bipolar, depression, anxiety, schizophrenia. Headaches and migraines are something we see a lot with a problem with histamine breakdown. We've also got neuropathies, MS, Alzheimer's, Parkinson's. There's a lot of research on these conditions. I've got some references at the end of these slides. Okay, so we need to understand what can affect the methylation cycle. Okay, so stress. This is a big one. Okay, so stress actually depletes the body of methyl groups. So if you're very stressed, even if the pathways are working well, you're using up all your methyls and then you don't have enough for the breakdown of histamine, for liver detoxification, for balancing neurotransmitters, for making myelin. So we need to really understand that stress plays a massive role in the problems that occur with methylation. Now, heavy alcohol consumption is also a big problem because it depletes your B vitamins, and the methylation pathways rely heavily on B vitamins. So the cofactors for MTHFR enzyme are B2, B3. You need B12, obviously, to carry your folate. We also need B6 to lower homocysteine. So if you're low in Bs, you're going to have problems with methylation. As I mentioned before, folic acid, which is the synthetic form of folate, blocks the uptake of your natural folate. So we want to be avoiding that. Environmental toxins, they place a huge burden on these pathways because what's actually happening is they're depleting your body of glutathione. Okay, they're also causing a sort of a burden on the liver. So glutathione is also used as part of liver detoxification processes. Bacteria, viral, fungal parasitic infections in the gut. This is so common these days. They cause a depletion in glutathione because they're sort of upregulating the immune system, causing inflammation. So you need a lot of glutathione to sequester the free radicals that happen with that. As I was saying, homocysteine can be lowered due to this, and you don't have enough homocysteine for methylation. Issues and inflammation in the gut's also going to reduce your absorption of your B12, which is very important for the utilization of folate. Simply having inadequate B12 intake. Okay, so B12 only comes from animal protein. So vegans and vegetarians are very susceptible of having low B12. As I was saying before, poor gut health is going to lead to the malabsorption of essential nutrients required for methylation. Now, zinc and B6 are also really important for these pathways. So the enzyme that you need to use your B12 is reliant on zinc, and the enzyme that takes homocysteine down the CBS pathway, the CBS enzyme, is reliant on B6. So here we have zinc and B6, which is people with pyrols will know all about that. Pyrols depletes the body of zinc and B6, and so does an overload of oxalate in the body. So oxalates are in foods. They're very high in nuts and seeds, also high in spinach. So people that are juicing and having green smoothies with a bunch of spinach every day might actually be depleting their zinc and B6. And people are having way too many nuts and seeds, often on paleo diets, can lead to a problem in oxalate and B6 zinc deficiency. Okay, so I thought I'd actually talk about some key blood tests that are really useful for understanding what can potentially be going on with methylation. So, these are some of the tests that I get my patients to do regularly. So that will include the full blood count, biochemistry, iron studies, B12. So we'll break down that into serum, active, and methylmalonic acid, tissue B12. We look at serum folate and red blood cell folate, fasting homocysteine, plasma zinc, serum copper. So red blood cells, this is one of the most commonly ordered tests, and it provides us with a lot of information about our red blood cells and because red blood cells actually carry oxygen around the body. And there are key markers when looking at red blood cells that give us clues as to potential issues with the methylation pathways. So low hemoglobin, so in males that's under 140, in females 135. So this is the iron-containing protein that carries oxygen in the blood. If you have a deficiency in hemoglobin, this can indicate a B12, a folate, or a B6 deficiency. We also look at mean corpuscular volume. So this is a measure of the average volume of a red blood cell, and it can, if it's high, it can actually indicate a B12 or folate deficiency, where if it's low, it can indicate a B6 or an iron deficiency. So as you can see, just having a look at these tests can give you a bit of an understanding of where the problems may lie. Now, mean corpuscular hemoglobin. So this is the average mass of hemoglobin per red blood cell. High levels can indicate a B12 or folate deficiency. Low levels can indicate a B6 or iron deficiency. We've got mean corpuscular hemoglobin concentration. So this is the measure of hemoglobin in a given volume of packed red blood cells. So low mean corpuscular hemoglobin concentration can actually mean a B6 or an iron deficiency. So iron studies. So iron, this is a really big topic, and discrepancies on a full iron panel need to be investigated really thoroughly. But generally what I'm looking for is we want women and men serum iron to be between 9 to 17. Ferritin, which is iron store in the liver. So for premenopausal women, we're happy, if it's close to 50, it rarely is, it usually sits way under that. Postmenopausal women, we're looking at say 100 to 263. Iron is involved in many processes in the body, including red blood cell formation. It's essential for thyroid production. It's also very important for the production of your neurotransmitters. Okay, so the amino acids that go on to make your neurotransmitters in the brain are heavily reliant on iron for that process. So we can see how important iron is for mood. So here are white blood cells. So these are our immune cells. So these guys give us huge clues as to what is going on with your immune system and inflammation and your need for glutathione. So our white cell count is the total number of white blood cells. So if it's high, sort of over 7, this can indicate an acute infection. It can be bacterial, viral, or a parasitic infection. If it's low, sort of under 5, we're looking at more of a chronic inflammatory condition. This does give us indication of, what's going on with homocysteine. Is it being pulled down that CBS pathway? We'd really need to know what your homocysteine levels are. Neutrophils. So these are the white blood cells that are first on the scene of an infection. High over 6 normally sort of indicates directly a bacterial infection. If it's low under 4, this is more of a chronic viral infection. A parasite can also indicate a potential B12, B6 or folate deficiency. So the lymphocytes, these are another part of the immune system that produce T cells and B cells. Low, under 2, we need to think, is there an active infection? Or it could potentially be chronic bacterial, viral or parasitic infection. And again, is it a B12, folate or B6 deficiency? Okay, monocytes. So these guys are the major producers of pro-inflammatory cytokines, interleukin-1, interleukin-6, and these help the body deal with infection. When we're looking at high levels, sort of over 0.7, this is particularly indicative of chronic inflammation in the gut. Okay, chronic inflammation in the gut is a big problem for nutrient absorption. Okay, iron, B12 can be quite depleted in these nutrients if there's a lot of inflammation in the gut. And the eosinophils, these are raised in allergic reaction. So over 0.3, it is like, do you have an allergic reaction to a food? Is there a food allergy? Can also indicate a parasitic infection. Okay, so here we're looking at our biochemistry. So one of the things I look at is the anion gap, which is a marker of actually how acidic we are. Okay, so to calculate the anion gap, you need to add sodium and potassium together, and then you subtract that by adding chloride and bicarbonate together. Now this will give you your anion gap, and the ideal level is between 10 to 12, often higher, and it indicates acidity. Now, problem with that is that our enzymes prefer an alkaline environment. And the other issue is when we're acidic, we're using a lot of calcium and magnesium to try and alkalize our system. And to do that, our body often takes calcium and magnesium from our bones. And that's not obviously terrible. That's not good at all. Magnesium, calcium will really help regulate your stress response. Both nutrients together can be really calming. Another marker I look at is GGT. Now, gamma glutamyl transferase. Now, this has got to do with glutathione. Okay, so the role of GGT is to reconstitute glutathione. Ideal levels in men are under 30 and in women under 20. So when GGT concentrators are sort of above this sort of low normal range, excess GGT can degrade glutathione, okay, causing a depletion in this really critically important antioxidant. Okay, so when glutathione is depleted and only insufficient amount remain, we're unable to protect our body's vital organs from oxidative stress. And this is when damage starts to occur. So over time, this process can lead to a vicious cycle of irreversible cell, tissue, and DNA damage. Okay, so here's our folate. There are 2 tests available for folate, serum folate and red blood cell folate. Okay, so when we're looking at serum folate, we want levels over 25. Red blood cell folate, looking at levels over 1,000. But what we don't understand is that these tests don't indicate what type of folate it is. You need to therefore question your patients. Is it dietary intake of folate? Is it coming from folic acid, so wheat products, processed foods, breakfast cereals fortified with folic acid, or is their diet sort of rich in green leafy vegetables? So it's really important that we question. If it's high in the serum, the person doesn't consume a lot of folate, then this is an indication, this potential indication this person is not uptaking the folate into the cell and could potentially have an MTHFR gene mutation. Okay, so B12. So there are 3 measures of B12. Serum B12, which measures both the inactive and active form of B12. So levels should be over 500 picomoles per litre. We've also got serum halotranscobalamin. Okay, so this is active B12. This measures specifically the fraction of B12 which enters the cell for metabolic activity. Okay, active. Levels need to be over 128 picomoles per litre. And we've got methylmalonic acid. So this is a functional measure of B12 status, and raised serum methylmalonic acid is evidence of a tissue B12 deficiency. So this is quite a serious depletion of B12. This test is often only ordered once a patient has tested low in serum and low in active. It can be tested both in the blood and the urine, and we know that the urine test is actually the most accurate for testing tissue cellular B12 deficiency. This test is actually done as part of the urine organic acids testing. So last but absolutely not least is homocysteine. So as I was saying before on the pathway planners, homocysteine is involved in 2 essential processes in the body. Firstly, the production of SAM for methylation, and secondly, the production of glutathione, your body's major antioxidants. These are 2 vital processes in the body. Okay, so we need to understand what homocysteine is, and the ideal level is 7. Okay, so when homocysteine is too high, it can be due to folate deficiency, an MTHFR gene mutation. It can be a B12 deficiency, a B6 deficiency. It can also be due to renal impairment. Smoking actually increases the risk of high homocysteine, and there's certain pharmaceutical drugs that can raise your homocysteine. So this is some of the reasons that homocysteine can be too low. Okay, so sort of getting under 6, like down, you can really down to like 4, 5, 4, 3 even. So what can cause this is inflammation and oxidative stress caused by infection, autoimmune conditions, and tissue damage. So this is really using up your body's glutathione. And since the production of glutathione requires homocysteine, an increase of demand for glutathione can lower your homocysteine levels. Simply by having low protein intake, okay? So, homocysteine is actually made from methionine, and methionine is an amino acid, okay, that you get from eating protein. Poor digestion and inadequate hydrochloric acid, okay, so you need proper gut function to absorb your protein and utilize your amino acids. Simply from taking too much methylfolate, methyl B12, and B6 in a homocysteine lowering product for too long can lower your homocysteine too far. I see this a lot in clinic where a patient's put on a homocysteine lowering supplement without even having their homocysteine tested. It might first of all be perfect at 7 already, or it might already be too low. They're put on these homocysteine lowering supplements and they feel worse and worse and worse. Also, taking pyrrole compounds with really high doses of B6 for too long. I've seen this also as well, where it's just pulling homocysteine down the CBS pathway because the enzyme cofactor for the CBS pathway is B6. Okay. So, that's also, homocysteine's not last. We're going to actually talk about zinc and copper. This is a big, big, big topic. So I'm just going to cover some real basics. Okay, so plasma zinc and serum copper should always be tested together, as ideally we'd like them to be a 1-to-1 ratio of about 15 to 17. This is because zinc and copper are capable of decreasing the absorption of the other in the digestive tract. Okay, so we often see copper high, and what can cause that is inflammation, as well as excess estrogen. So estrogen dominant women often have high copper. So women on the pill will definitely have high copper. It's often sort of 25, 26. When you're pregnant, your copper is really high as well. We also know that zinc can be low due to the use of the oral contraceptive pill. Now, absorption of zinc is inhibited by excess sugar intake, insufficient hydrochloric acid in the stomach, and pancreatic enzymes. Gut inflammation and allergy are also going to deplete the body of zinc. Excessive calcium intake also impairs zinc absorption, and zinc also competes with iron for absorption, so you're best to take them away from each other. High oxalate foods, nuts and seeds, spinach, sweet potato, for some people, or particularly if you're having them in excess, can bind and excrete zinc from the body. Okay, so we need to understand that ensuring that the proper zinc-copper balance is as close to 1-to-1 as possible is essential. So we make sure we need copper, but we need the zinc. Zinc's a really important cofactor, the MTR and the BHMT enzymes. These enzymes are involved in the recycling of homocysteine to methionine for methylation. Okay, so all of that said, that complicated pathways and testing that we do, there is so much that we can do with diet and lifestyle to improve our methylation. So firstly, simply, we can increase the intake of folate-rich foods. So these include green leafy vegetables, lentils, barley, beans, eggs, liver, and sprouts. We need to eliminate folic acid from the diet, so that's fortified in Australian wheat, many commercial processed foods and retail supplements. Supplementation with methylfolate may be necessary for some people. Methylfolate can have some serious side effects, so it really needs to be done in conjunction with a practitioner that's trained in MTHFR. Avoiding medications that block B12 absorption. So these are the proton pump inhibitors such as Nexium and Somac, which are given out like candy for reflux. So that will definitely lead to a B12 malabsorption and low B12. I see it often. We need to be ensuring we're eating adequate amount of B12 rich foods. So that's animal protein, eggs, meat, chicken, salmon, fish. If you're a vegan or vegetarian, you really should be looking at supplementing with B12 daily. We also need to be avoiding inflammatory foods. They include sugar, fried food, processed foods. Gluten can be particularly bad for some. If your immune system doesn't like gluten, that's going to cause inflammation. Excessive red meat intake, particularly grain-fed meat. You're better off with organic grass-fed meat. Again, excessive dairy intake, caffeine and alcohol, obviously, are inflammatory, unfortunately. We can increase the intake of our anti-inflammatory foods. Green leafy veggies are amazing anti-inflammatories. Nuts and seeds, as long as you're not having too many or have an oxalate problem. Fish that are rich in omega-3 fatty acids such as salmon, and ginger and turmeric are beautiful anti-inflammatory herbs that you can eat. Antioxidants, okay, so antioxidant-rich foods, blueberries, raspberries, turmeric, chia seeds, they're actually quite high in omega-3. Brazil nuts for selenium, broccoli, goji berries, and green tea are all nice foods that are rich in antioxidants. We also need to be reducing exposure to herbicides and pesticides. We need to eat organic where possible, and that includes organic fruits and vegetables as well as organic grass-fed meats and animal products. These herbicides and pesticides place huge toxic load on the body. So hard for your liver to detoxify and putting a real burden on your glutathione needs. Okay, again, reduce heavy metal exposure. Okay, so reduce intake of fish that are more likely to contain mercury. So that's tinned tuna, farm, salmon, barramundi, prawns and swordfish are particularly high in mercury. We also need to avoid cooking in aluminium cookware, and obviously avoid stripping paint in old houses. We can look at detoxifying the home, so avoiding plastics and tins lined with BPA. We know BPA actually damages DNA. We also need to be looking at using natural cosmetics and cleaning products and drinking filtered water. And last but absolutely not least is because we know that methylation is used for the stress response, we really need to be managing our stress. And whatever that is for you, some people need to just go for a run, get out there and run their adrenaline out. Other people prefer to sort of cook a beautiful meal for their family, just spend time with their friends. Meditation daily is an amazing practice for calming the nervous system. Breathing techniques, deep breathing, yoga, and in just ensuring you're getting adequate sleep. This sleep deprivation causes a huge stress on the body. So these are just some lifestyle tips that you can take away. This is all my references at the end. But that's it from me. Thank you for listening, everybody.